Welcome to the video lecture series Digital Filter Design and its Application. My name is Dr. Anilesh Dey, Associate Professor, Department of Electronics and Communication Engineering, Narula Institute of Technology, sharing this course with one of the renowned professor, Professor Dr. Solil Kumar Sarnal. Professor Dr. Solil Kumar Sarnal, retired professor and head, Department of Electronics and Telecommunication Engineering, Jadavpur University. Presently, Professor Sarnal working as a professor in the Department of Electronics and Communication Engineering, Narula Institute of Technology. This is lecture 4. In the lecture 3, I already discussed the magnitude response of the Butterworth filter, and also you can go for the derivation of the order of the filter, which is capital N. And in this particular figure, it is the response of the magnitude response of the Butterworth filter, where omega p is the passband frequency in radians, omega s is the stop band frequency in radians, omega c 3 dB cutoff frequency in radian, epsilon equals to parameter specifying allowable passband, lambda equals to parameter specifying allowable stop band, passband attenuation is alpha p, stop band attenuation is alpha s. And already also discussed the formula of the n, which is equals to n greater than equals to log root over of 10 to the power 0.1 alpha s minus 1 divided by 10 to the power 0.1 alpha b minus 1 divided by log omega s by omega p. So this is already discussed, so I directly entered to the problem statement. For given specification alpha p equals to 1, alpha is equals to 30 dB, omega p equals to 200 radian per second, omega is 600 radian per second, determine the order of the filter. We know that A equals to lambda by epsilon, and lambda equals to root over of 10 to the power 0.1 alpha s minus 1 divided, and epsilon equals to root over of 10 to the power 0.1 alpha p minus 1. So A equals to nothing but a square root of 10 to the power 0.1 alpha s minus 1 divided by 10 to the power 0.1 alpha p minus 1. So put the value of alpha p, alpha s, omega p, omega s. So if I put the value of alpha p and alpha s, I can find the value of the A equals to 62. And if I know that k equals to nothing but the omega p by omega s, if I put the value of the omega p by omega s over here, so k equals to 1 by 3. So we know that n greater than equals to log a by log 1 by k. So that is greater than equals to log 62.115 divided by log 3. It is equals to 3.758. So rounding of the n to the next higher integer, we get n equals to 4. So answer of the question is the order of the filter equals to 4. Now I explain the step to design the analog Butterworth Lopez filter. So step number 1. From the given specification, find the order of the filter n. Round off it to the next higher integer. Find the transfer function hs for omega c equals to 1 radian per second for the value of n. Calculate the value of the cutoff frequency omega c. Now formula of the cutoff frequency omega c equals to omega p divided by 10 to the power 0.1 alpha p minus 1 whole to the power 1 by 2n. And step 5 is that find the transfer function HAS for the above value of omega c by substituting s by omega c in HS. So these are the steps to design the analog Butterworth Lopez filter. Now come to the problem statement. Design an analog Butterworth filter that has minus 2 dB passband attenuation at a frequency 20 radian per second and at least minus 10 dB stop band attenuation at 30 radian per second. Now from the given specification alpha p equals to 2 dB, I can take the mod value, and alpha is equals to 10 dB and omega p equals to 20 radian per second, omega s equals to 30 radian per second. We know the formula of the n equals to n greater than equals to log root over of 10 to the power 0.1 alpha s minus 1 divided by 10 to the power 0.1 alpha p minus 1 whole divided by log omega s by omega p. Now put the value of the alpha p s omega p omega s in the equation. So it is nothing but the log root over of 10 minus 1 divided by 10 to the power 0.2 minus 1 divided by log 30 by 20. So that is equals to 3.37. So this is the step 1. Step 2 is the round off to the next higher integer. So rounding of n to the next higher integer. So n equals to 4. Now step 3, find the transfer function of hs for omega c equals to 1 radian per second for the value of n. The normalized low-pass Butterworth filter for n equals to 4 can be find it out from the table. H is equals to 1 divided by a square plus 0.76537 s plus 1 into a square plus 1.8477 s plus 1. We know that omega c equals to omega p whole divided by 10 to the power 0.1 alpha p minus 1 whole to the power 1 by 2n. So put the value of alpha p and n over here because right now the value of n equals to 4. So omega c equals to 21.3868. Now the transfer function for omega c 21.3868 can be obtained by substituting s equals to s by 21.3868 in hs. So finally hs equals to 1 divided by s by 21.3868 whole square plus 0.76537 s by 21.3868 plus 1 into 1 by s divided by 21.3868 whole square plus 1.8477 into s divided by 21.3868 plus 1. That means we have substituted the value of x in the previous equation and with s by 21.3868. Now this is the final transfer function of the Butterworth filter. Now here I designed the Butterworth filter in the MATLAB. So this is the command, the CLC clearer. Now I have to initialize the alpha p, alpha s, fp, fs and f is the sampling frequency. So alpha p equals to 4, alpha s equals to 30, fp equals to 400, all are written in hertz, fs is 800, f equals to 2000. Now omega p equals to 2 into fp by 8, omega s equals to 2 into fs by 8. Now to find the cutoff frequency, n omega n is the command which is available in the MATLAB, but what within bracket omega p, omega s, alpha p, alpha is from there we can find out the omega n. Now system function, it is written for the Butterworth filter b comma I equals to butter n comma omega n. I just written the range of the omega, it is a 0 to pi. H comma omega m equals to frequency z b a omega whole, m equals to absolute h, an equals to angle h. Now I want to plot this thing. Subplot 211 plot om divided by pi comma 20 log m, and I can give the grid command Y level equals to gain in frequency, X level equals to normalized frequency, subplot 212 plot OM divided by pi, N for angle, comma grid, Y level define the phase in radians, and X level is the normalized frequency. So this is the output. So this is the magnitude response. This is gain in dB. It is a normalized frequency, and it is the phase response, phase in radian. It is the normalized frequency. So this is the output of the low-pass Butterworth filter. Now, in this particular program, I denoise the signal using the a low-pass Butterworth filter. So I just go for the flowchart. How can I design the program? Start, I generate X is a sinusoidal signal. Then generate Y is an acknowledged signal. Then I added these two signals. So I can define a new signal Z, which is combination of X plus Y. Then I can go for the Fourier transform of the Z, go for the spectral analysis. Now design the low-pass Butterworth filter for n equals to 4 and take the input of the filter equals to Z, find the output of the filter, and then stop. This is the flowchart. The first, to generate the X equals to sinusoidal signal. So I declare the Fs equals to 500, F equals to 10, N equals to 0 to 1 by Fs to 1, X equals to sine 2 pi F into N subplot 231 plot N comma X. So I generate the X. So this first step is over. Now I generate the random signal. Y equals to random 1 comma length X subplot 232 plots N comma Y. So this is the generate the random signal. So it is a, when we can generate the signal, after that adding the two signal, length should be the same. That's why in this here I can return the length this. So if this length is not matching, so MATLAB will give you the error. Next, generate the Z equals to X plus Y and subplotting once again. Now N equals to length of Z. So NEFT equals to 2 to the power next power 2 of L. So I can go for the point of the FFT. That's why I find it out what is the point of the FFT. So if the total point is the here, suppose it is a 501 is total point is the, so it is going for the next 2 power. So N equals to next 2 power of the 501, that is 512. So Z FFT is the absolute FFT Z comma this length. The frequency equals to Fs by 2 into line space 0 to 0 comma 1 comma the point of FFT divided by 2 plus 1, subplotting this thing. Now I generate the filter. Order of the filter is the 4, N equals to 4, omega C equals to 10 into 2 by Fs. Where from I get the 10, I explain when can go for the output. BA equals to butter N omega C low pass filter, that's why I written the low, and I can go for the figure frequency ZBA 1024 Fs, H omega frequency ZBA 10024 Fs. I'm again subplotting. Now this is the filter. After designing the filter, I can put the input Z in the filter and get the output. So Z filter equals to filter B A Z. So Z is taken as the input, subplot and plot the output. Now this is the output. Now this is the original signal X. So first I generate the X. Now I generate the noise Y. This is a random signal. Now this 3 I can add it this signal plus this signal. So Z equals to X plus Y. So this is a Z. Now I can go for the Fourier transform of this signal Z. So for whatever, if I zoom this thing, so I can find it out that there is some there is some DC value, and this is the high level frequency, that is the frequency at 10. So I have to pass this frequency up to 10. Rest of the frequency I am neglecting. So I can design the filter in this way. This is a magnitude response, and finally I fed the signal to the filter, and finally it is a noisy signal, and fed I can get the original signal. So this is up to this lecture, today's lecture. So these are the references. So these are our contact numbers. This s_sandal@itpd.org. This is Sandal sir's email ID, and this is my email ID. So it is a length of lecture 4. Meet you in the lecture 5. Now, if you like, please subscribe our YouTube channel.